All right. Howdy, welcome to the Smart Grid Center webinar on Full-Fidelity EV integration study using large-scale combined transmission and distribution simulations. I'm Andrea Kishney from the Smart Grid Center. First, let me ask you to send a clarifying question, just repeating what Jonathan said for the record, in the Q&A window anytime to get it addressed during the presentation, or raise your hand with the hand button in the Zoom window for in-depth discussion at the end of the presentation. The presenter today is Dr. Jonathan Snodgrass, Senior Research Engineer at Texas A&M Engineering Experiment Station, working under Professor Thomas Overby in large-scale electric power systems. He received his bachelor and master's degree at Texas A&M and master's and PhD degrees at University of Wisconsin-Madison, all in electrical engineering. His primary research area is in power system network planning and resilience, with current projects focusing on light, medium, and heavy-duty EV integration using combined transmission and distribution co-simulation. His other research areas include modeling impact of high-impact low-frequency events, such as geomagnetic disturbances and electromagnetic pulses on the electric grids, power system optimization, and microgrids. He also worked at Zachry Engineering Corporation in Amarillo, Texas, designing simple and combined cycle power plants that use natural gas for 2 years. Jonathan, take it away.
Awesome. Thank you for the introduction, Andrea. There you go. So with me also is Dr. Ann Shu. So this project, the work on electric vehicle integration and modeling is a joint collaboration between ElectroTempo and the Texas A&M Smart Grid Center and the Texas A&M University. So I think we actually have most of the team on here. So shout out to them for all their very hard work, because this, as you will see in a few minutes, this is a very in-depth project. There's a lot of technical analysis, a lot of data, and a lot of modeling. So the team here at Texas A&M is myself and Professor Tom Overby, who I see on the call. Hey, Tom. Diana, Tom's senior PhD student. Jess Wirt, who has recently graduated. Actually, she's graduated for almost a year or two now, but time flies. And Lyric Halo. He is a new master's student in Tom's group and worked with me on undergraduate research on this project. And at ElectroTempo, Ann is the PI, Mike Lycan, and then there's others as well that were involved. So I'll give a brief overview of the work, and I'll turn it over to Ann for her to describe the sources of EV data and modeling on their end, and then I will discuss the Texas A&M results, analysis and results. And so as a preview of coming attractions in August, we're going to be doing a fully joint webinar where the ElectroTempo team is going to go into a little bit more detail on their data analytics, their modeling, their EV siting and projections, so that way we can get a little bit better sense of how the data is created. But for now, we'll see kind of a high-level overview. So as everybody knows, the energy transition is happening. Renewables are being integrated at an increasing rate, and electric vehicle adoption is increasing. But as y'all probably know, it's a long time to deploy EVs. Unlike traditional power system analysis, where you have very siloed operations with distribution and transmission, load serving entities, and in some way you want this because you want to have a competitive market. So you want the generating companies to be ring fenced from the transmission owners and operators if you're in a market environment like ERCOT. But the problem with EVs is that you span all of these. You have EVs, electric vehicles, connecting at the distribution system. You have them connecting at the sub-transmission level for a bank of smart chargers. And if you have fleet charging, you can have EVs have their own dedicated transmission substation. And so it takes time to order and deploy EV. It takes time to deploy and order EVs, whereas traditionally, you can order and receive a fleet of diesel trucks in a fairly quick manner. But if you're deploying an EV fleet, you need to determine if you need to build the infrastructure that's required. If you have an existing fleet and you have an existing, say, bus barn or a parking structure, you need to figure out if the electric grid at that location can handle the increased load. And if not, you have to either decide whether you need to move or whether you're going to build the necessary infrastructure. So it's a very collaborative, or needs to be very collaborative and much more in-depth process. So the solution involves more than just grid analysis and more than just transportation, which is why we have both ElectroTempo and Texas A&M University working together on this. So you have the charging demand and infrastructure piece of things. You have the electric grid overlay, which I'll be discussing in more detail. And you also have the emissions impacts, which I will briefly touch on, but that could be a whole nother webinar itself. So as an overview of the project, we were building off of some existing work that we have done in the past from urban truck modeling, charging stations, and we're adding in new analysis of travel demand, larger scale, and looking at combined transmission distribution over a larger part of Texas. And I'll get into that in a little bit. But so what we received from ElectroTempo was 96 scenarios, 24 hours, an hour long each. So 24 hours, hour resolution, 96 scenarios, and we conducted transmission and distribution co-simulation. So we looked at OPF, minimizing transmission, operational constraints. So we used we assume balanced three-phase on the transmission system, which future work might show that might not be fully, the more single-phase loads you introduce and the more variability, you might start breaking some of the balanced three-phase assumptions, especially when you have more harmonics from EV chargers. But that's not the subject of this webinar. But for now, we'll just assume a balanced three-phase, and because for now, that's a very safe assumption on the transmission system. But the distribution analysis, we did an unbalanced three-phase full distribution system power flow, looking at single-phase, two-phase feeders, and as well as full three-phase feeders. And I'm going to hand it over to Anne to give a brief introduction of ElectroTempo and her work, her leading the team, the bit of explanation of where the data is coming from and what the charging data represents. And then I will take it back over to present A&M's results. Let me see if I can now. I think, Anne, you should be able to click through the slides. If not, let me know by like using your forward backward keys.
Yeah, it works great. Thank you so much, Jonathan. Hi, everyone. My name is Anne Xu. I'm co-founder and CEO of ElectroTempo. ElectroTempo is a software company focused on EV charging infrastructure planning and intelligence. And by that, we really do two things. One is to project EV charging demand. How much will there be, where, and when? And the other side is to optimize the infrastructure to meet that demand. And to do that, we collaborate with partners like the Smart Grid Center at A&M on the grid side. And we also work with commercial real estate companies to optimize on the charging infrastructure side. So as you can see, because of the scope of our work sitting in the middle of the e-mobility ecosystem, connecting electric utilities, commercial real estate, and fleets, our customers span across all three sectors. So what we, I think it goes without saying that we're all here talking about electrification now because we definitely see the adoption trends that's especially been it's cemented by policymaking. Most recently, the US EPA finalized the phase 3 emissions rule, which pretty much requires that there is a large portion of the fleet that will be zero emissions vehicles to reach the emissions goals. However, to reach those goals, charging infrastructure really needs to keep pace. But there are several hard to reach nuggets, fleets being one of them, transportation corridors, and multifamily charging. So our analytics really set out to address these key areas. And in this webinar, what we're going to talk about is medium and heavy duty truck fleets, but we also have work ongoing identifying multifamily charging projects, also in collaboration with A&M's Smart Grid Center working with PG&E to help with multifamily charging. So to give you a flavor, of course, Jonathan's going to dive into the technical details of how this has worked. This project has been implemented in the sense of large-scale simulation. I wanted to give you a quick flavor of how we actually have taken the methodology and findings of this work to put into real-world, utility decision-making. So most recently, we've been working with a coalition of Texas utilities. They banned themselves as the Texas Public Power Corridor, including CPS Energy in San Antonio, New Brownsville's utility MBU, Austin Energy, and LCRA. So we've identified potential truck charging locations and the associated charging load, given different adoption levels along the I-35 corridor between Austin and San Antonio. And this work has stemmed from the work that in this project between us and Jonathan's group funded by DOE. So exactly what did we do and why did we set out to do what we did? So fundamentally, what we're trying to do is to provide a puzzle piece to the long-standing tradition of grid analysis, including load forecasting and grid impact, grid planning. Traditionally, the electric power industry has done a great job forecasting load on commercial, residential, and industrial sources. But with transportation, that's an entirely new source. It happens to move around. It's hard to pin down. It requires completely different data sources. And so what we set out to do, and by the way, I have a PhD in transportation systems engineering, and my background has been, roadway in infrastructure planning and demand forecasting. So what I was able to do by founding the company really was to do the translation between transportation data and, energy data that the electric power industry can use. Specifically for trucking, the challenge comes in that even in the transportation system, in the transportation industry, data is very scarce when it comes to medium and heavy duty vehicles. If you think about it, in Houston, for example, I think Houston has about 5.5 million vehicles, last I checked, probably more now, but more than 5 million of those are light-duty vehicles. So on the roadways, you get a lot of observation of light-duty vehicles, how they behave, how they travel, where they go, but the truck portion of it is small. But trucks are very important when it comes to energy, because when they electrify, they'll have large battery packs, their energy requirements are high, and when they have to charge, they typically have to charge very fast. So the power requirements are high as well. And therefore, from an energy perspective, we have to pay just as much attention to trucks, if not more, as we have traditionally to light-duty vehicles. Yet there is not enough information on trucks. Trucks typically are not registered where they operate. That's a big challenge. And trucks also can have so many different use cases. They move long distances, but they also have local operations. So how do you identify them? So our approach is really to rely first and foremost on the rich knowledge base and data sources in the traditional transportation data sources, in particular the travel demand models. And along with those, there are freight models and truck models that we can we can use. But we also enhance these models with innovative methods. Specifically, we use AI and property tax records to identify, pinpoint where truck depots are, such that we can really identify where hot spots of truck operations are, and fuse it into a dynamic demand simulation based on origin and destination patterns to build this region-wide charging demand map that can be then taken to the grid site for Jonathan's group to do grid analysis. So for this project specifically, as Jonathan mentioned, we ran 96 different scenarios on charging demand, right, given different assumptions on charge rate. So what if these trucks charge at 100 versus 200 versus 300 kilowatt rates? What if it's peak season versus shoulder? Charging logic, this one particularly, because right now there's a lot of talk about managed charging. What if trucks just charge upon arrival versus if there's some kind of management influencing when they charge? In this case, we just simulated if they just charge starting at midnight and then at different locations, especially with those high power locations. Does it make a difference if we could move one charging hub from one location to another to lessen the load on the grid? So from there, we produce the outputs that is hour by hour charging demand at a very high spatial resolution at transportation nodes, which can then be mapped to grid nodes for analysis. So you may ask, okay, you did all of this, model building, data analysis, how do you know it's correct? So the way we validate our data and also to meet DOE's requirements, accuracy requirements, we basically took our agent-based bottom-up approach and validated from the top down, both at the traffic level and at the charging demand level. So we made sure that from our simulation, the traffic out of our simulation is within 10% difference from observed traffic patterns. And then the resulting charging demand, when it gets aggregated up, it's within 20, DOE's requirements was actually within 20%, and we beat that by a large degree. So our difference was only slightly more than 10%. So with that level of confidence, I'll then hand it over to Jonathan to talk about the grid side.
Perfect. Well, thank you so much, Anne. So I asked Anne, Dr. Xu, to come and speak because traditionally, as most of y'all power system engineers know, we know our power systems very well, but anything outside of power systems, we treat as black boxes. And especially on the transportation side, most of us think of our vehicles, unless you're car aficionado or you like getting your hands dirty under the hood, you turn on your car, it runs, and you don't have to worry about it. You take it down to the mechanic and it works. But most researchers do the same thing on the transportation side of things. I've read plenty of papers where one or both, either the grid, so I've read transportation papers where the grid is assumed to be this perfect ideal, voltage behind reactance. And those who know transmission systems go, haha, that's silly. Why did they do that? But I've read papers written by electrical engineers who don't partner with transportation experts like Anne, who just use a Weibull distribution for the arrival times and a Gaussian distribution for the state of charge. And they don't even tell you really where they get the parameters for those. So they just make up parameters. It's better than nothing, but not by much. And so, I mean, it's okay to test in electrical engineering. It's okay to test an algorithm, but it's not going to be useful for any sort of real world applications. And so what the goal of this project was to do, that's why my title of my talk is Full Fidelity, Large Scale Electric Vehicle Integration. And I'll camp here on this slide for a second, because if nothing else, for my academic friends on this call, make sure that you incorporate full modeling of both transportation and the grid. Now, for our grid friends, I know they know that's the case. And for our transportation friends, they'll say, finally. So the other thing for my academic friends is to say, make sure that you do something that's bigger than a small scale system. And I'll go back a slide in a second. So most academic research is proof of concept. Is this possible? Not is this practical? So this, which there's definitely time and place for, is this possible? Because if you prove that it's impossible, or prove, we engineers do proof by simulation. If you prove that it's possible, then you can start moving it down the chain of R&D. So we here at A&M like to do both research and development. And so by that meaning, we prove that it's possible, but also prove that it's practical. And so on the practical side, if you can take your algorithms and your simulations and you can prove that it works on a utility-sized grid, then it actually has the promise of seeing the light of day in a control room or in a planning operations, either grid planning or grid operations. So going back for a second, most of my utility friends know that, and this is starting to change, but historically, most grid operators have operated their grids independently. You have a distribution system operator, you have your distribution operations center and the transmission operations center, and they're typically in different buildings, different locations, and they only typically call each other if things are getting bad. And otherwise, the distribution system load is usually assumed as an ideal constant power balanced three-phase load that shows, if you're a transmission system operator, you see a balanced constant power three-phase load and no harmonics. You assume you do a per phase analysis. You use Newton-Raphson power flow or transient stability assuming positive sequence modeling. And for the distribution system operators, they usually view the transmission system as either an infinite bus or some model incorporating the short circuit ratio, but it's some variation of perfect voltage source behind some form of reactance, whether that's subtransient reactance for fault studies, or whether that's synchronous reactance for the point of interconnection, the strength of the grid. But it's just assumed that the transmission system can supply as much power as the distribution system needs. And for most of the planning of the grid, it's been totally fine. But as all of us know, in the last 10 years, things have been changing drastically. Instead of having a few dozen new large-scale generators, or maybe 50 total per year, some of them being peaker plants and some of them being baseload, we're now looking at hundreds, if not thousands, of individual wind and solar installations. And as you know, those are variable. And so there's the change on how new generators are interconnected, how day-ahead market is starting to function. Things are starting to move, and realizing that now you have this. This talk is not about this, but I'm prefacing this as to why we have to start considering bridging the gap between transmission and distribution. And we have, with the increase of DERs, with the increase of customer generation, so rooftop solar, with the addition of some microgrids, the whole assumption that distribution system is purely passive is no longer true in some growing number of cases, but also for the transmission system too, as things become more variable, as we start integrating more variability, as we start having legacy grid equipment that is at the end or nearing the end of its rated lifespan. Doesn't mean that it can't be used beyond that, but if it was planned for 50 years and we're still using it, you have to start accounting for some level of derating on your transformers. So my point is that for many, many reasons, we need to start, especially for electric vehicle integration, we need to consider a combined T&D co-simulation, not just assuming that the opposite system is a black box or a perfect model. And as I mentioned, most papers either ignore the fine details, the dynamics, transportation dynamics, or electric grid detailed modeling. They either ignore the distribution system, they treat the transmission system as overly simplified, or they grossly oversimplify the transportation side of things. So now that I've fully overemphasize almost the importance of this study. The reason why I do that is to point out that the effort that we went to simulate things on a large scale with full fidelity modeling is worth it, because otherwise, how can you trust your results if you're doing something that is cross-domain like electric vehicle modeling? So as a little bit of background, those who are not very familiar with the Texas A&M research here, starting almost a decade ago, actually, Dr. Tom Overby, Professor Tom Overby, my boss, and several of his graduate students, now Professor Adam Birchfield, started creating synthetic transmission models. And I started actually around 2016, a little bit later than them, up at the UW-Madison with my advisors, Chris DeMarco and Bernie Lesure. And the project was started out of RPE. It was the goal of creating these large-scale open source transmission and distribution system models that would update the IEEE, the old legacy small IEEE test cases that unfortunately many people are still using. So if you get nothing else out of this talk, please stop using the old IEEE systems for your final paper. You can use them as a proof of concept if it works, but move on to something a little bit bigger, at least on the order of hundreds of buses, if not thousands of buses. The cases exist. They're out of Texas A&M. There's some out of Wisconsin. There's some from Georgia Tech. Use larger models, please. And our industry friends would probably say amen. The combined, yes, Andrea, I see a hand.
There is someone in the Q&A window asking to speak a little slower, please.
Ah, okay. Thank you. Thank you for pointing it out. When I get excited, I start speaking quickly. So thank you. Thank you. Thank you. So we built on that transmission system modeling, the work that we did, before I got here, that was done here at Texas A&M. I started in 2021. Before Texas A&M, or before I started, we're building on the work that now Professor Adam Birchfield and Professor Tom Overby and their groups have done on transmission, the work that NRail through their Smart DS program has done on the distribution system. And so if you see here on the left, let me see if I can get a spotlight. Perfect. Okay. So on the left here, those who are from Austin will recognize this as more or less the street map of Austin. So without going into all the details, there could be a whole multi-hour webinar on how these synthetic distribution systems were made. But the short is it's mostly using OpenStreetMap data combined with some innovative GIS and modeling techniques to create a realistic but not real distribution system model that incorporates existing right-of-ways, mostly streets and highways, and plots out a distribution system that has an aggregate load that matches very closely with the real ERCOT load. That synthetic distribution system is connected into the transmission system, and each of these squares here represent a substation in our synthetic 7,000 bus combined transmission and distribution system model. Now, you might say, well, the one on the left and the one on the right are a little different. The one on the left is a zoomed in version of an older model that has 230 kV and 345 kV, I believe, or 138 and 230 in the Travis County region. The reason why I use this picture is because it's more zoomed in and you can see it. The one on the right is the one we use for this project. We're specifically looking at Dallas, Fort Worth, Houston, and the I-45 corridor. So going right near my hometown of College Station, Texas. So you might ask yourself, why not use the real grids? And we have access to the real grid models. Why not use those? Well, we can't publish them. And I couldn't, I'd have to check everyone, make sure they had an NDA before they jumped on this webinar. So the goal of these open source models is to test algorithms. It's not necessarily these open source T&D models cannot be used for EV placement. You can't say, oh, we should put EVs here. This specific location is good. But what these synthetic models are very useful for, and what we used them for, is to validate algorithms. Does the framework work? Is it solvable? Can we get useful results? And what we did is compare percent changes. If this is your baseline, and then you have introduced electric vehicle load, what's the percent increase in the cost? And that we can say with very high certainty, it would be very similar to what we would see on the real transmission grid. Now, as a caveat, we're not doing dynamics right now. We're not doing N-1 contingencies yet, but we're doing, to date that I know of, the largest combined T&D modeling project that probably has ever graced ERCOT, if not the world. Unless the national labs have been doing something that they haven't published yet. But I couldn't find anything in the literature that was this large. So what we're looking at is 7,000 bus transmission grid on the ERCOT footprint, combined with about 6,500 distribution transformers with almost 4 million distribution nodes total. And so keep in mind, as we said earlier, we have 96 scenarios of hourly resolution to 24 hours. I can't do the math right off the top of my head, but that's a lot of data. So as we've mentioned, this study is multiple orders of magnitude larger, and you might ask yourself, well, Jonathan, well, Dr. Snodgrass, why did y'all do something so big? Wouldn't something smaller work just as well? Well, it would work, but not just as well. Because if we're going to do large-scale EV integration, we need to simulate the effect of the large-scale EV integration. And you might ask yourself, well, why couldn't you subsample? Well, like Dr. Shu Ann mentioned earlier, we're simulating large-scale trucking. So you've got trucks that frequently drive from Dallas to Houston, and they start in different locations in Dallas, and they end in different locations in Houston. And so we need to simulate the combined grid, and we also need to simulate both the transmission level and the distribution level. Because you might ask yourself, well, why not simulate a small piece of the distribution system without the transmission system? Well, as you know, if a truck leaves in Dallas and then comes and charges in Houston, the power for that distribution system has to flow somewhere. And even though each feeder is independent, it's connected by a transmission system, which that transmission system itself is interconnected with all the other distribution systems. So we can't just island in a sense. And also for this particular project, because we're looking at heavy duty trucking, we're also looking at, slowing down, sorry. We're also looking at both distribution level loads below, I think we chose 3 megawatts, which is kind of a rule of thumb roughly. Anything above 3 megawatt peak, we assigned its own dedicated transformer connected directly to a substation. We have transmission loads we're simulating and distribution loads we're simulating. So a T&D, combined T&D simulation was necessary. And I'm seeing some Q&A pop. Give me 1 second while Andrea, I'm seeing some questions pop in, but I don't see the questions themselves. If they're clarifying questions, do you mind turning on your camera and reading them off to me? Because I can't, there might be some technicality that I can't seem to open up the Q&A while I'm presenting.
I think these are more, well, Tom's suggestion to have the new paper posted by Sanjana on his website, but I will get this link and post it for everyone. The other is a more, I think it's discussion.
Perfect. Okay.
Question, so that would
Awesome. Yeah. So if you have questions, if you have a clarifying question, just because it might be easier to address while I'm going, just pop it in the chat. And if you have a question for the end, feel free to put it in as well. I had the chat open, but I realized the Q&A section is separate from the chat, but I will continue on. So the combined T&D automation that we're doing. You realize I'm only on slide 17, but some of these slides I can go through a little bit more quickly. So we have published several papers on this. So if you have more in-depth questions, we can discuss at the end, or you can read our papers. But we use Helix as the controller. We use PowerWorld Simulator for the transmission system analysis. And we use OpenDSS for the distribution system analysis. And we send voltages and substation load from Helix. From the distribution system side, we send the updated updated voltage and current. We send the upgraded load to PowerWorld, which then computes the substation voltage and current from the transmission system, voltage angle, voltage magnitude, and sends that back to the distribution system through Helix. And so we have a couple papers we're in the process of writing, and one that details this a little bit more. My power system expert friends know, very familiar with your classic OPF. Shout out to Carlton and team. I'm an author on this paper, so I can use this formulation. But this is on the right is one of the many forms of AC OPF. Those who know it well can immediately look at it and go, I know what that is. But those who are less power system inclined, our transportation friends and our policy friends, on the left, you can see in plain English kind of what these equations are modeling. So we're minimizing the generation cost subject to various constraints, such as you don't overload your transmission lines, The power flow constraints are the power flow equations, meaning the physics equations, energy must be conserved, conservation of energy equations. The line constraints, meaning don't overload your transmission lines. Generators have mins and max. You have bus voltage constraints, and there's numerous other ones, but these are the primary ones we simulated. So this is the high level on the capital cost. So I'll preface a couple things. One, like I said, is we're looking at deltas. So we're looking at run the base case with our synthetic grid, and the raw number, the raw operating cost number is less meaningful than the change between 0%, which is not shown, and the delta between 0% market adoption and 25% market adoption. And then each of these delta, this is cumulative. So later slides, we'll see deltas of deltas. So what that means is that these numbers, 25% to 100%, are the change from baseline, from base case, to 100% to 25%. The next slides will show what happens what's the change from 25 to 50, because I'm sure you're probably doing that math in your head right now, as I was and would be doing. So the several things to notice are you have to look at a yearly EV adoption cost. So we'll detail this a bit more in our paper. So we didn't do a year-long analysis. We did one 24-hour period. And because we wanted to compare operational costs with capital costs, which the payback period is typically 10 to 50 years, depending on how you do it, maybe around 20 is the average. So I picked a representative day, which is about May 3rd, which is fairly close to the average ERCOT, the average yearly load, multiplied it by 365 to get a rough an idea of what a scale would be compared to a year. And as all of our friends who are involved in markets know, the operating cost of the grid is quite dominant if you're not looking at major grid upgrades. And in this case, because we have a fairly well-designed synthetic grid, that's the one critique we received of our synthetic grids is that they're a little bit too well-designed, but it's easy to take a well-designed grid and make it a little harder to solve. But so most of y'all might say, these numbers seem a little low for the transmission system capital cost. You're probably right, and we're going to rerun some of this analysis on the real grid in future work to just compare those numbers with our synthetic grids and use that results to update our synthetic grids. Perfect. Okay. Sanjana just posted, and I'll mention that at the end. So, but if you're looking at a grid that doesn't require a lot of capital cost upgrades, the cost of running the grid is by far the most dominant factor, and that makes sense from an operational perspective. But one thing that's interesting is the cost of upgrading the distribution system is much higher than the cost of upgrading the transmission system, based on the assumptions that we made. Of course, this is not a perfect study. And you might ask, well, how did you get all those numbers? Great question. Read our paper. Not in a bad way. We're going to be publishing. I mean, I would take an entire hour just to explain where those numbers, the numbers themselves came from. But we're going to be publishing several papers. Myself, Diana, Lyric, we're all writing, not at this very second, but we're currently writing several papers explaining much more detail, explaining the methodology and the justification of these numbers. But the best way to think of them as looking at a delta. And so several things you'll notice is that as EV adoption increases, the rate of change increases. It almost exponential, but thankfully, 100% adoption is as high as we can get. I'll keep going before I pause to see if there's any questions. So this is, like I mentioned, the delta of the delta. So when you go from 0% to 25% market adoption rate, and what is the change? And so as you notice, as your EV adoption rate increases, your cost difference increases, which makes sense. You run an OPF, you dispatch a cheaper generation. And as you increase the load, your marginal cost increases, therefore increasing the marginal cost of EV adoption. So then the interesting comparison gets in when you start looking at comparing this charging upon depot arrival compared to charging beginning at midnight. You would expect to see a bit of a higher change. And the answer is you do when you look at different factors. But it's a fairly sizable amount. I mean, granted, this is all of them averaged. So this is an average of the 25, 50, 75, and 100%. It's hard to put 96 scenarios and summarize it in one table. And the paper will make multiple tables diving into a bit more of the results. But the average savings was around $100,000 almost, because this is the dollars and thousands. So $100,000 over a 24-hour period is not a small amount of money, just for changing your charging from charging at depot arrival to midnight. One thing that's interesting, which was counterintuitive to me at first, but then makes perfect sense, is when you charge faster beginning at midnight, it makes it cheaper. And you think, wait a minute, isn't concurrent load worse for the grid? Yes, concurrent load is worse for the grid at peak. But if you're charging off peak and you charge faster, it's cheaper because large trucks take a while to charge because the batteries are large and they have to cover long distances. The charging is going to last more than just a few hours. It's going to be lasting for multiple hours. And so if you charge faster, you can get more of your charging done during the wee hours of the morning instead of having to push into 7, 8, 9, 10 later in the day when the cost of the grid goes up. So now granted, some of this might change, as you incorporate N-1 contingencies, as you incorporate the variability of renewables, which we are doing both of those in future projects. But it's interesting, semi-counterintuitive, but it makes sense. Now, of course, charging upon depot arrival makes sense that it'd be more expensive. If you charge faster when people show up from their day of driving, it's going to cost more. This one, the negative number, it's negative on average. There were several scenarios, especially the higher market adoption rate, where charging faster upon depot arrival was much more expensive. But like I said, just having a summary slide is hard to do with lots of data. I'm going to pause here. And actually, I'm going to keep going real fast, and then I'll open up the floor for questions, because I know there'll probably be quite a few questions about this. So capital cost finding, like we said, it's fairly low compared to the operating costs, but that's also because we didn't incorporate contingencies. I'll highlight a couple of interesting findings, and these slides in the recording will be available if you want to dive into them more. Like before, the marginal cost, in a sense, the marginal increase is also increasing when the charging increases. It's also, you have less, you have fewer overloads when you charge faster, when you charge at night as a midnight beginning compared to upon depot arrival, which makes sense. Your capital cost is also lower, which makes sense. So the capital cost, let me back up. It's hard to put a number to how much it would cost to correct an overload. But throwing up a megawatt mile of overloads is less meaningful for most people. So I converted that to a dollar amount using some reports I'll detail in my paper of typical per megawatt mile transmission cost of upgrades. So these capital costs are coming from correcting the overloads that result from the OPF, because you have, you might ask, well, it's infeasible. How can an OPF solve? Well, Power World is great because it can solve a relaxed version of the OPF where it's still a feasible power flow solution, but it violates some of the transmission line limits. But of course, charging upon depot arrival, the faster you charge, the more overloads you have. Environmental cost, I will look through this. Actually, I'll kind of more focus on the key findings, and I'll leave the numbers for you to look through on your own. So the rate of emissions increase went down as market adoption rate increased. So what does that mean? So as market adoption rate increases, yes, okay. So let me pause here for a second. So it's interesting. This right here is the opposite of the capital and operational cost. Is that as you integrate more EV, the non-CO2 emissions difference decreases. And you might ask yourself, wait a minute, how can that be? How can that be? I haven't dove into it entirely, but my initial theory is that coal is cheaper the synthetic cost curves that we use, because this is synthetic grid. The synthetic cost curves that we use have coal is cheaper than baseload coal, be cheaper than baseload natural gas, because we were using natural gas prices from several years ago, from like a year or two ago when they were a lot more expensive. Now, of course, it's a lot cheaper. So we're in the process of updating our synthetic cost curves. But coal is cheaper to operate, but more polluting. But as the EV load increases, the natural gas in our model, the natural gas plants start getting used more, like some of the peaking units start getting used more. So they're less polluting, but the natural gas peaking units are more expensive to operate. The CO2, it's interesting that the non-CO2 emissions increased when you started charging at midnight. You ask, well, wait a minute, how is that happening? The cost is going down because you have increased concurrent load. You have increased concurrent load at midnight, and therefore you have to commit more of your generators at midnight, whereas instead you would typically decommit your peaking units that are less efficient, and you might ramp down some of your coal units at night to incorporate more renewable generation that's higher at night. But for the sake of time, I'll continue on. So you might ask, how can we charge more efficiently? So you can create rate structures. And so this is preview of future work. As Ann mentioned, there's a lot of talk about managed charging, and we're working on some managed charging projects and proposals. And so I'd love to talk to any of y'all who are interested in joining those projects offline. But a simple delay EV charging. So if the transmission bus LMP is above a certain threshold, delay EV load. And once it drops below that, you pick up the previous EV load. You basically pick up the delayed load and shift it accordingly. So operational costs, delaying the EV load always resulted in cost savings, which makes sense. The reason why most of the cost savings were when you have the okay, let me pause for a second. Charging at midnight saw higher cost savings compared to charging at depot arrival, which is, you might think, counterintuitive but the problem with the way we simulated it was it's a 24-hour simulation that starts at midnight. It goes from midnight to midnight. And because of that, because of time and budget limitations, every project has those, everyone knows this, we didn't have wraparound charging. And so we ran from midnight to 11 p.m. If you had charging beginning at 4 or 5 p.m., it only got bumped until midnight and didn't wrap around to the next day. So future work could incorporate, some sort of sliding scale if you're doing managed EV charging, which we will for our future projects. But so some of the results are shown here. This is the percent savings looking at no managed charging versus a simple first order approximation, a simple managed charging strategy of charge during low grid demand, such as beginning at midnight. So as the market adoption rate increases, the savings from the rate structure from the delayed EV charging increase. As the charging rate increases, your savings increase. And as like I said, if you're doing it beginning upon midnight because you have concurrent load, and beginning upon depot arrival, as you charge faster, your savings become less because you have more concurrent load to deal with. So the transmission capital cost, this is very intuitive. So if you're delaying EV charging at transmission nodes that have high LMP, for the majority of the time, we were able to completely eliminate, almost entirely or entirely eliminate the overloads. And therefore, the high LMP, as y'all know, you're like, of course, the power system market people know that the high LMPs indicate congestion or hopefully not in real life overloads, but in which case, in our case, it wasn't overloads because we're doing a planning study. But if you're able to do managed EV charging or delay the charging, then based off of price signals, you're able to eliminate or either very much reduce or eliminate those overloads, therefore eliminating the need for upgrades to the transmission system. For the sake of time, I'm going to just jump to the numbers, and you might say, those numbers are all over the place. Yes, exactly. That's because right now, distribution system operators don't have a market. And so if there's an overload, which normally there shouldn't be, normally there's not, but if something happened and numbers got entered wrong, the overload shows up when a fuse pops or a breaker trips, and then you go investigate and you figure out, wait a minute, too many people integrated EVs, electric vehicles on this in their home without telling us, and we just overloaded the distribution feeder. Or if it's at the feeder head level, you can look at some SCADA data. My point is you don't have there's not yet a distribution system market. So if you have overloads, there is no, in practice, I'm sure there's literature on this, there's no distribution system LMPs, distribution node LMPs. And so therefore there's no price signals coming from the distribution system to the transmission system to incentivize delaying the load. So that's the future work. And I'll skip the environmental piece. In the slides, you can look through it. So future work is to look at co-optimization framework. So not just optimize transmission system and treat the distribution system as full-scale modeling, but do optimization on the distribution system side. So either use like some sort of price signal. So either create a price signal in the sense that if the distribution system is starting to near or exceed its limits, send some sort of either price, some sort of signal back to the transmission system or back to the distribution system operator, say, you want to incentivize your people on this feeder to delay their charging. And so we're going to look at future work. We're going to look at both top down and bottom up approaches. One is control of, if there's a central entity that's managing the charging. The other one is you send out price signals to either directly to the chargers or to the consumers to say, how much flexibility are you willing to give us in order for a reduced price of your EV charging? So with that, I'm going to open it up for questions. If you have more questions than we can answer in the next few minutes, feel free to email me. The slides and the recording will be available, and I'll let Andrea read the questions. I can't pull them up. And if it's a question for Anne, please indicate whether your question is for me or for Anne if you're in the chat or in the Q&A.
Okay, from the Q&A, Marco from Milan, Italy is asking how you are modeling load profiles for domestic, but also for industrial users on the distribution grid. That is clearly impacting a lot on the e-cars grid hosting capacity you are calculating. I'm not sure.
Great question. So I'm going to defer, and if you send me an email, I could probably, if you can't find the paper, if you can send me an email, I will try to direct you to the paper. So the distribution system modeling was done by NREL. I think Brian Palmentier and his team, Brian Matthias Hodge was part of this as well. They had an entire methodology to create those distribution system loads. They went through several iterations and several updates to make them as realistic as possible. So to answer your question, I don't know right off the top of my head, but there's papers that are published about that. If you look up NREL Smart DS, you can look at their publications.
Next question. Are there currently any monitoring system at EV charging stations on the highways or at high-end customers?
That's a good question. I'm assuming that they're getting some sort of the EV chargers are getting some sort of telemetry and data feedback at some level. Whether it's getting shared with grid operators, I don't know. Do you know, Anne?
Yeah, it depends. It depends on whether it's a separate meter. But I do know that for NEVI chargers, there is a required data sharing protocol. So as the new highway corridor NEVI chargers come online, hopefully we'll get more insights into how the chargers are utilized.
Thanks, Anne.
Next question, would the charging stay consistent at 200 kilowatt or 300 kilowatt, or would it start high and decrease as the battery has a higher charge state? Did you take this into account?
Yeah.
Good question.
Yeah, it's a really good question. But as Jonathan mentioned, at this level, we're assuming they're, charging at a constant rate. But our joint next level of work will factor in the second by second, charging profiles, how the power ramps up and down with the chargers.
Good question. Who was it that asked that question, Andrea?
Sorry?
Who asked the last question about the charging rate?
Jonathan Picker.
Ah, okay. Hey, Jonathan, good to see you.
Okay. Next question. Can you give some details about how you associate the arrivals matrix of the traffic model to specific grid node? Are you including in the analysis the already in place charging infrastructure? Next question, what if an arrival zone has more than one substation in it resulting from a synthetic model? Could you please motivate more what you discussed before about the need to include the transmission level of the grid instead of just the distribution grid?
Yes. Okay. Yeah, that's like 3 questions in one. Can you read the first
And
question? please? I
one
think
more
that's
at the
directed
end
towards
that you
Anne.
can answer later.
Yeah, I think the first question is directed towards Anne. If you can read that one again. The second one I think is more of a my question because it's on the mapping side of things.
Can you give some details about how you associate the arrivals matrix of the traffic model to a specific grid node?
Yeah, so that one, I think Jonathan is actually that's the crux of our joint model. If you flip to the map where we showed Austin, for this particular research paper, we used a I believe I think Voronoi tessellation to map the nodes. Because of the synthetic nature of this model. But in real world, as I mentioned before, we apply this to real world cases, we can actually map, so we can actually go down on the transportation side, go down to the address level, and then map it to the feeders given the grid topography.
So I guess, can you just speak super briefly about kind of how you determine where the likely location of the EV chargers is, Anne? Yeah. I think that's might have been what the question was hinting at just a little bit.
Yeah, so right now, because the charging infrastructure is not prevalent, and especially since this project is about truck charging, and truck charger are basically non-existent so far in this country, most of the country. So we had to make some assumptions as to, the basic assumption is that the chargers are going to be where the major truck operations are. And we actually, so come to our August webinar where we talk about the transportation side more. So we divide the truck operations into depot-oriented operations versus highway operations. So your local traffic versus over the road. And the depot charging is going to mostly happen at the depot location, which is actually a reality wherever, especially in California where the truck charging is already happening. And then there are hub locations along the corridors. And the highway corridor location, we actually chose the I-45 location based on a report published by the NCTCOG, the Dallas-Fort Worth Metropolitan Planning Organization, where they published a plan and consider different potential locations for I-45 charging locations. So that's how we went about it. And the whole idea, again, here is there's going to be a lot of questions about where truck charging is going to happen, and we have to be able to answer the what if questions, and that's why we developed this dynamic simulation to allow us to answer those questions.
Let me suggest to answer the rest of the questions in email, and there is one person who wants to ask orally, Thuan Pham, and I allowed you to unmute yourself. So please unmute yourself and ask your question. Thuan Pham.
So just a quick question on this model. Have you looked at the way the battery, let's say the degradation of the battery will affect the charging rate? I mean, are you going that detail in the level of the model? Because certain battery can charge faster, slower, depending on how fast, how the condition of the battery is at. So.
Not right now. I would say it's that would be the next level of study.
So I'll briefly just fire through the 2 of these questions. So the longer question, please feel free to send me an email on that. So George is asking about looking at outages, impact of outages. The answer is not yet. Contingency analysis is the next step. Time-based programs like ProMod. So ProMod is a commercial program. We're using something similar, but it's Helix, PowerWorld, and PowerWorld Simulator and OpenDSS. And so we are computing congestion. We're just using different tools than ProMod. And so Shin, your question is a good one. We should dialogue with Anne offline on that. So I think that's all the questions that I see.
Thank you so much. We are up at the hour. So thanks for this very interactive and great webinar and all the feedback and questions. And hope we can continue it in August with your next presentation. Let me mention that our next webinar will be presented by Dr. Lachie on the 12th of June. And it's also a very timely, interesting topic on exploring the capabilities and limitations of large language models in the electric energy sector. So please watch out for the detailed announcement coming soon. So until then, thanks everyone for the great participation, and take care and goodbye.
Bye, everybody.
Bye, everyone. Thank you.